Hello everyone and welcome back to Educator.com. I'm Dan Fullerton and in this lesson we're going to talk about conductors. So let's start with some of our objectives. To begin with, we're going to try and understand the nature of electric fields and electric potential in and around conductors. We're going to explain how all the excess charge on a conductor resides on the conductor's surface, not in its bulk. Explain why a conductor must be an equal potential. And finally, graph the electric field and electric potential inside and outside a charged conducting sphere. So as we start talking about charges in a conductor, we have to remember that charge in a conductor is free to move until there is no E field. Charge is free to move until the electric field is equal to zero. So if we have all these free charges in a conductor and they're free to move, they're going to migrate to the area of the lowest possible energy state, get as far apart as possible, and that usually puts them on the surface. If they are moving, they're no longer in equilibrium. If there are electric fields inside the conductor, the charges would move. So when you have a conductor and it's in equilibrium, all the charges have already distributed themselves so that they're not going to move anymore. There is no net internal electric field, otherwise they'd keep moving. So the electric field inside a conductor is zero. We can think about that if we draw some sort of random conducting shape here. If we have some charge plus Q that we put somewhere on that surface, the charges are going to repel each other and they're going to go and move as far apart as they possibly can in order to minimize their potential energy. That puts them all on the outer surface. We could also go and draw a Gaussian surface inside a conductor. Let's put our Gaussian surface something like that. As we draw our Gaussian surface, we could look at it from Gauss's law perspective, the integral over the closed surface of E dot dA is the enclosed charge divided by epsilon naught, but we just said that the electric field must be zero, therefore the enclosed charge is going to be zero. All the charge has to reside at the surface. Not in the bulk of a conductor. Now, field lines are all going to run perpendicular to the surface. Perpendicular to the surface. If they weren't perpendicular to the surface, there'd be some component that's parallel to the surface, and the charges would then move. And as we just said, the charges already moved in the conductor until the electric field is zero. So electric field lines have to intersect that conductor at 90-degree angles. They have to be perpendicular. So let's look some more at the electric field at the surface of a conductor. If we look at just the outer surface, let's make a note of that. Looking at just the outer surface, let's take, using Gauss's law, the integral over the closed loop of E dot dA is our enclosed charge divided by epsilon naught. And let's assume a surface where we have some symmetry. So we'll say that our charge is sigma A. Therefore, the electric field times the area is going to be our enclosed charge, sigma A, over epsilon naught, or the electric field is equal to the surface charge density, sigma, divided by that constant, epsilon naught. What this really means then is you're going to have the largest electric field where you have the largest charge density. Which is common sense as well, but probably worth stating explicitly here. Now, let's talk for a minute about hollow conductors.